Hi, so I'm Paul Beckwith. I'm at the University of Ottawa. I'm in the Laboratory for Paleoclimatology. I'm a climate system scientist, so I try to look at all of the different pieces of the climate puzzle and try to connect them together to see where the climate has been in the past, where we are now, and try to determine where we're heading in the future. I think we're undergoing abrupt climate change right now. We're seeing extreme weather events around the world and a disruption in the heat transfer patterns from the warm equator to the cold poles. And I have a degree. I did a Bachelor of Engineering degree in engineering physics at McMaster University, and also did a master's degree in laser physics. And more recently, I've been at the University of Ottawa for about 8 years. I've been in the PhD program for some of those years, but right now I'm on leave so that I can focus on my videos, which I produce a few YouTube videos per week typically on the climate system, and also on a blog, paulbeckwith.net.
Okay. Now, you did mention a couple of words in introducing yourself that made things click. You study the climate differential between the polar and the equatorial region. And that's really critical. And that's something that people don't understand enough about. And that's kind of where we're going to be working today.
Yes. People know the equator is hot, right? And, it's tropical, it's very warm. Temperature doesn't change too much. Like if you live in a city like Ecuador, named after because of its proximity to the equator, the monthly temperatures might change only a few degrees. The monthly average temperatures, plus or minus a couple of degrees all year round. It gets 12 hours of sun, 12 hours of darkness, it's warm, and the poles, of course, for many reasons, the poles are colder. Mostly it's a geometry problem, because the poles are colder, the heat wants to move from the equator to the poles, and it can do that in two different ways. It can do this by ocean current movement, or it can do it by atmospheric jet stream, atmospheric winds and jet stream.
Yeah.
Yeah, so in the oceans, it creates these ocean patterns of circulation where you have the Gulf Stream moving northeast towards Europe, and as it moves north, it becomes colder, and the water is salty because there's a lot of evaporation, so it's saltier, it's heavier, and it sinks down, and then you get these thermohaline circulation ocean patterns, and that carries about a third of the heat that moves from the equator to the Arctic, say, is carried by the ocean currents. So there's a Gulf Stream, of course, off the eastern US, and then there's the Kuroshio Current off Japan, which is the Pacific version of the Gulf Stream.
And those are less known terms, so
yes, they are. And so, of course, in the atmosphere, the jet streams exist because of that heat transfer from the equator to the Arctic. And because of the rotation of the Earth, they get there's deflection to the right for any moving object and moving entity in the northern hemisphere, and the Coriolis Force, it gets larger and larger as you get further and further north. So the curvature becomes greater, and you get a concentration of air, and you get these jet stream patterns. Now the problem is that heat balance is all changing now.
So the Coriolis Force, can you just say a couple of words about what the Coriolis Force is?
Yes, so the Earth is rotating, okay? It's rotating from west to east, okay? That's the rotation of the Earth. And if you're at the equator, you're the furthest away from the center of rotation. You've got the radius of the Earth, you're away from the center of rotation. As you move further north, you're getting closer and closer to the axes of rotation. And at the North Pole, you're actually right on the axes of rotation.
So the further north you go, the slower your land speed is by the rotation of the Earth. The closer to the equator, the faster you're traveling through space, essentially.
Right. You know, and this idea of the effect on moving objects isn't that, it is fairly recent. Like basically in World War I, we could fire these dreadnought battleships would fire huge shells, and they would always miss the enemy ship on the right-hand side. So they built mechanical computers to correct, and the amount they would miss would depend on their latitude. So because when you fire a shell, if you're at the equator, the west to east motion of that shell will be very high, and as that shell moves further and further north, the west to east motion is the same. It's going to slow down a bit from air resistance, but the Earth's speed will have decreased because you're getting closer and closer. So it effectively, objects deflect to the right in the northern hemisphere. So the winds that are moving northward will deflect to the right. And this is why the jet streams get focused and concentrated and move from the west to the east.
And the Coriolis Force is then the term used for that effect?
Yeah, it's the term used for that effect. It's like a hidden force is acting on the object, pushing it to the right. Right? It's like a hidden force, and it's because of the rotating frame of reference of the Earth. It's like an ant on a turntable. You know the old record turntables. If you had an ant that was moving across on the turntable, then it would appear to be going in a curved path to an outside observer. Okay, anyway, we'll talk soon. Okay.